All right, let's get started. Hope everybody had a good weekend. So let's just do some announcements, reminders as we're barreling towards the end. So of course, don't forget, next week is Memorial Day. Thank you. So no class on Monday. That's just a federal holiday. And so we probably won't have a quiz next week. That's what I'm thinking. Since we'll have to try to squeeze in a lecture on Wednesday. Sorry, I was just kind of looking at the calendar because I was debating about giving your midterm or your final on like week 9 so that you would have like all of week 10 to kind of do it. So I think that's still on the tentative docket there. Sorry, let me pull up your syllabus. So just in terms of where we are, so we have our solutions lab this week, so we're on week 8. We can read that. So next week we'll do our last lab, and then week 10, so we'll have a lab final. So it'll be, I think, fairly easy. You'll just have to do some like minor lab manipulation, and then it'll mainly be lab checkout, so just making sure all your equipment is nice and clean in your drawer. And like I said, I'll probably give you your final take home so you can work on it week 10, and ideally give it to me like Friday in my mailbox week 10, so then I can just focus on grading that last week. And then you guys won't have anything to worry about then, week 11. So we'll have to see when we can squeeze in some makeups. So probably if we had to do a makeup lab, it would be Monday. It would have to be week 9. I'll say Monday, week 9 for... Wait, not week 9. Week 10, since week 9 is Memorial Day, sorry. So anyone that needs to do makeups, probably that last week will be the time to get it done, just because we won't have next Monday, and then we're basically at the end of the quarter. All right. And then I should mainly be caught up on grading. The only thing I didn't do was the credit back on the exam. So people have turned that to me. I've made a pile so far, and I'm just going to process them all at the same time. But otherwise, I'll try to hand back all your work today. All right, so let's continue then with our chapters. So again, Chem 104 is a good survey of a lot of things. And so now this chapter, we're going to focus on gas laws and kind of the basics of that. And so, of course, this is just a quick reminder of our different states of matter. So, of course, we learned that we have a solid state of matter. Again, we'll think about ice, okay? Ice has a fixed shape and a fixed volume. And then we know, okay, it can become a liquid if we add some more heat to it. And now it just conforms to our container. And so now a gas, we mentioned some of its properties. So, of course, it expands to fill our container. But we can also add words like compressible. And so we can, kind of put it in a container, compress it, make it smaller. You could compress it all the way back down to a liquid. And so this is kind of what this chapter will focus on is this compressibility and how we can change our gas properties. And so now just defining what a gas is. So of course it is a phase of matter. And we mentioned, okay, this is a high energy state, so we put a lot of energy in there. And so they're moving randomly and very fast, so there's cycling around. And so now we have to make some assumptions. And so this is our kinetic molecular theory of gases. And we're kind of making, again, some assumptions. So this is more for an ideal gas, we'll say. And so we'll discuss kind of what do we mean by ideal gas, and we're looking at these set of conditions, and then kind of where the deviation occurs, or at least we'll talk about it. And so from our kinetic molecular theory, so gas particles move in straight lines, and so we're just kind of assuming that they don't really occupy a lot of space. And we're also not accounting for any intermolecular forces, which we'll get to in this class. So we haven't discussed that. And so, so we're just kind of treating it like little billiards. So they're going to move in straight lines, right, until they hit another particle or the wall. And so again, they go in straight lines. And so we're going to look at those collisions. So those collisions are essentially what makes our pressure. And so now we can think about how this works in the context of a balloon. So if you have a balloon there, let's analyze what this means. So we have our balloon, and of course it is filled with air. And the reason why it stays inflated is, of course, right, you have all the air inside the balloon, and so it's beating against the inside of your balloon. And of course, it's counteracting the force of your atmosphere. So, right, you have, of course, the atmosphere beating down on your balloon, but you've filled it up such that it stays inflated, right, keeping that same pressure in there as it exerts pressure inside the balloon there. And so we can, like I said, we'll quantify this, or we can quantify this. And so pressure is also described, if you take in some physics, so force over the area. So you can think about, again, how this extends to your balloon argument. So if you have, right, a smaller balloon, then it takes a lot less air to get a lot of pressure in there, right? So smaller surface area, and so this area you might want to change to kind of surface area in your mind, since it's where it's striking. And of course, right, larger balloon, you guys know you have to put more air in it, or if you were to put, right, the same amount of air, it would have less pressure, since less force. All right, so now we're kind of seeing then that gas pressure is a result then of the constant movement of this gas. So, right, it's just the result of all those collisions, so beating down. And again, we'll get to the math in a second in this chapter, but the pressure depends on a few factors. So obviously the number of gas particles, so how much air you blow into a balloon. And then, like we mentioned, the volume of our container or balloon, so smaller balloons versus larger balloons. And then the speed of our gas particles, which kind of goes into temperature. And so this is kind of what I was saying too, is we're making some assumptions here, again, with kind of this ideal gas. And so we're saying that collisions of our gas particles are said to be elastic, so perfectly elastic, meaning no exchange of energy occurs. So again, just assuming that they meet and bounce right off, versus an inelastic collision, right, like kind of two cars colliding together, where the energy is going into crumpling the cars rather than just bouncing off. All right, so that's part of, again, just kind of our assumptions there. And we'll look at more assumptions because, again, we're assuming no intermolecular forces, but this will come up. And so now let's look at some units of pressure. So again, dimensional analysis is our friend. And so let's look at where the units of millimeters and inches are derived from. And so this is a manometer here that allows us to measure our pressure. And so this is kind of a really old school traditional one. And I mean old school in the sense that it's a pool of mercury. So obviously mercury has a bad reputation. I actually don't think elemental mercury is that bad, but anyways, we won't go down the mercury rabbit hole right now. And so this is just a pool of mercury, and then this glass tube here is evacuated. So you can see it's under vacuum. And so this pool of mercury is, of course, experiencing all these collisions, right, of the atmosphere kind of beating down on the mercury. And so all those molecules beating down on our mercury drives it up this little glass tube. So the standard 1 atm of pressure, if you were to measure the height column, it would correspond to 76 millimeters, or of course in standard English units, right, 29.92 inches. So that's just a millimeter to inch conversion. So right, there's 2.54 millimeters equals an inch. So that's where that's from. And so usually we use millimeters of mercury. That's a common unit. So there's 760, again, millimeters of mercury. Or used very interchangeably is torr. So it's 760 torr is 1 atm. And of course you also have units of atmosphere, or atm. And let's look at our chart. So we have more units here. And so again, on an exam, you'd probably just be expected to be able to convert between the units, especially if I gave you a conversion factor. And so notice, so we have pascals is another unit, so that's Newton per meter squared. So 101,325. And then it's not on this chart, but we could also have kilopascals, which obviously just means, right, kilo. So 101.325 kilopascals. PSI, so usually you see this on your car. So typically a car tire is around 33 PSI. And so it tells you 14.7 PSI is 1 atm. And then like we said, 760 torr, or millimeters of mercury. We also have bar, which isn't used too much, but if you were looking up like the weather and trying to figure out like the local pressure, for some reason the weather stations always report it in bar. And so 1.013 bar is 1 atm. All right, let's practice a conversion. And let's do our car tire. So convert 33 PSI to ATM. We'll do ATM and torr for fun, so we can do a few conversions. All right, so what do we get? So how many ATM is 33 PSI? 2.24, that sounds good. I'm just setting up the work. And do we have 2.24? Excellent. Sorry, a little slow. Forgot to open my calculator. There it is. And then did we convert ATM to torr? So how many torr was this? 1,702.4. So let me write it out. So 760 torr, 1 ATM, and then, sorry, you said what?
1,702.4.
1,702 ATM. And could have left it at 1,700. Got a little awkward there with sig figs, so you might have to write it in scientific notation if we were being proper. And so that sounds good. Just typing it in on the calculator. And 2.24, sorry. Excellent. Questions on that one? Just unit converting, dimensional analysis. All right, nothing too bad. And so now we're going to get into the math. So it's starting to quantify those properties of gases and how they relate. And so the basic properties that we've been discussing are pressure. And so the standard units are an ATM, but I'll let you know when the units matter and don't matter. And so sometimes they don't matter depending on the formula. And then volume, again, typically in liters, we'll see where it matters. Temperature is the one thing that always has to be in Kelvin, so I might star this one. So temperature, it has to always be in Kelvin, no matter what. It has to go back to being thermodynamically relevant. So Kelvin, remember, goes from 0 and then all the way positive. So we have to keep our temperature positive or else we'll end up with wonky stuff. So I'll just say that. So need T to be positive. So always Kelvin. So no matter what. And then moles is typically, of course, our amount. So I think y'all know that or are starting to realize that about chemistry. And so like we've kind of hinted at earlier, so these properties are interrelated, so kind of going back to gases being compressible and all these different pressures. And so we're going to be able to, of course, manipulate the gas by changing these variables. And so we'll start off by just examining our simple gas laws. And I probably won't test you explicitly, so I don't tend to ask trivia questions like which one's Boyle's law. So I don't care too much about that, just examining the pairs and the relationships. But then we'll see that we can kind of summarize it with this gas law. But like I said, that's where we're going. And I think it becomes easier once we look at the combined gas law. And so it kind of starts off with this they were playing around with these different relationships. And so the main ones we'll look at are Boyle's, Charles's, and Avogadro's law. And so starting with Boyle's law, so Boyle and Hooke, and of course you can appreciate when this was, so pretty early, chemistry, if you want to call it that at the time. So they're just trying to experiment with J tubes, and J tubes essentially is just like a sealed tube. I'll show you a modern one. So basically, this can be used for gas experiments. So this is just a little needle valve. Like I said, I'm not sure what their equipment looked like back in the day, but kind of the idea is you have this valve where you can, open it to, usually you put a sample down here or an NMR tube, and then you hook it up, fill it up with gas. And then this is where you always have to be careful though. So I've known chemists personally who have condensed liquid into an NMR tube, and then it will explode because, right, if you obviously condense gas too much and you put too much liquid in there, and then obviously it's going to re-expand and could shatter that. So that's where gas chemistry, that's where the danger is kind of if you're not careful and you don't have a bleed out somewhere. But anyway, so they basically took these tubes that you could seal and change. And so kind of looking at this piston model, since it's a little easier to envision. So they trapped some air in their tube and then added mercury. And so that mercury is just working to increase the pressure on the gas. So again, just how you might add weight to a piston. And so they noticed an inverse relationship between volume and pressure, aka, so starting off with these conditions, so we have pressure at 1 atm, volume at 1 liter, and then if we half our volume, so now volume to 0.5 liters, our pressure doubles by twice. And so this is kind of the graph of that relationship. And then any guesses as to why the graph kind of does this bottoming out deal? So why would that be? Kind of what limits how much we can compress it? Yeah, the space, right? So at some point, those atoms do occupy space. And so yes, there's like a limit of how much we can compress them. So that's, again, going back to some of the assumptions of this ideal gas, of course, right? Ideal gas. And well, here's our formula, right? We just have this mathematical relationship. P pressure, our initial pressure, times our initial volume equals our second condition of pressure times our second volume. So again, we have this relationship, but again, we have to think about those physical limitations. So yes, at some point, this ideal gas relationship breaks down, and yes, gases do occupy some space physically. All right, so this is good. So again, I would start this relationship. So P1, V1 equals P2, V2. And this is where the units may vary. So as long as like pressure units are the same, so say as long as they match. So AKA, right, atmosphere with atmosphere, torr and torr. So these don't matter so much. Same thing with volume, right? It could be milliliter, liter, even really gallon. Not that you would see that, but so in these, doesn't matter since we're just comparing the initial and final relationship. And so again, inverse, and so let's again appreciate what that means. So pressure times volume is a constant. So as one goes up, the other must go down, or vice versa. And so we can think of other kind of applications or scenarios where you'd want to think about this. So has anybody ever done diving, deep sea diving or anything? One year I had one student who had experience with it, so I can share his story. And so I don't know how much y'all are aware about diving. I've never gone diving. But we can see, so of course, part of the challenge of exploring the ocean, as you may know, and remembering back from, when was that little ship that just exploded like a year or two ago? The deep sea submarine thing. Y'all know what I'm talking about. I can't remember its name. But obviously, so why it's so difficult to explore the ocean is so for every 10 meters of depth, a diver experiences approximately 1 additional atmosphere of pressure. Okay, so there's the problem right there, right, is there's an incredible amount of pressure. Again, going back to that deep sea diving thing, why it exploded or imploded. And so then, of course, if you're diving as well, this has implications, which we're dancing to. And so, okay, if you're diving at 20 meters, then you have approximately 3 atm of pressure. And so now kind of looking at this and where the bends comes from, and let's think about what's going on. And so if a diver holds his or her breath and rises to the surface quickly, the outside pressure drops to 1 atm. And so, this is a little extreme what it's saying. And so, of course, if you were to somehow keep your lungs shut, well, this is also why they say you should always be exhaling as you go up. And so it mentions what happens to our volume of air. So because our pressure is decreasing by a factor of 3, the volume will expand by a factor of 3, and of course, that could cause damage. What this isn't getting into is, again, like the bends. So let's really talk about what's going on. So obviously you have dissolved gases in your bloodstream. And so same thing applies to all those gases, right? So if they're under, 3 times as much pressure, that's also why they say, you have to rise slowly. So it's not just the volume in your lungs that you have to exhale, right? Obviously you want to be exhaling. But the other idea is you have to give your blood enough time to degas and make it, to your lungs to breathe out. Otherwise, so like I mentioned, I had a student in my class there who he was in the military, so that's why he had undergone some diving training. And he was saying that one of his buddies had come up too quickly, and then they did experience issues. So like blood vessels, I think, had kind of burst in his eye or something, so I think he had to go to the hospital. But that's just, kind of showing you that that's where the damage can happen is, again, right, you have your little blood vessels. If the gas expands too much because you rose too quickly, then of course that can damage or, damage obviously other internal organs. So that's what it means by the bends, and again, that's the physical hazard. And then if you start looking into it, because people do this as a sport too, like extreme deep sea diving. And I don't know like how they adapt their bodies or how their bodies get used to it, but that is a total danger where sometimes these people, because you do have to go obviously up and fast if you're trying to hold your breath with these extreme sports. And some people do suffer like aneurysms and strokes with these extreme sports with that danger. So, and yeah, and then we could go on a tangent too about like fish design and how they withstand all those pressures, but we won't go there right now. All right, let's look at this problem. So we'll try to practice our formulas. So P1, V1, P2, V2. And so now this is telling us how our lung works. And so, right, we inhale by increasing our lung volume. So your diaphragm, right, goes down to physically create more space. And so let's just say we have an initial lung volume of 2.75 liters filled with 1.02 atm. And so let's say we could just capture the moment when the diaphragm is down, right? We've extended our lung volume. And so what would be the pressure then in our lungs, right? And basically kind of, you can see how that's driving air into your lungs. But so what would be that pressure if we could just measure that? So let me know what you got. So I just wrote out our setup. So obviously our one set of conditions on the left side, second set on the right. And then, before you punch stuff into the calculator, just kind of mentally guess what the number should be, or at least, right, is it going to be lower, is it going to be higher? And so we know if our volume is increasing, then our pressure should decrease. So we expect, right, a smaller number. Always good to at least sanity check yourself. And so what do we get for our new pressure? That's where we get. So we got 0.863, so I see some nods. So 0.863 ATM there. And then, like I said, units didn't really matter. Of course, they just happened to be in liters and ATM, but we didn't need to do any converting anyways, even if they weren't. Okay, questions on that problem? So it feels straightforward. Oh, I forgot to mention, so I don't know if you have seen these before. They're kind of, at least I thought they were popular. And I posted a link in Blackboard. But this gas properties one is a fun one to play with. And so especially if you're at home and just kind of want to play with it, so we can see, so let's add some particles. And so then we can hold different things constant. So we'll just pick temperature since it's not in play. And so then we can see, right, we have our pressure, so 5-ish ATM, and then we can make our container smaller and appreciate how it almost doubles, right? And now we can half it again. And so this is just, like I said, a kind of fun tool that lets you play with these gas laws in real time. So it should already be on Blackboard, but otherwise you can probably find them with these PhET simulations by the University of Colorado. So they're super nice. All right, so we'll keep looking at our ideal gas laws. And so now we'll look at Charles's law. And so now this is a volume and temperature relationship. And so now we're saying that they have a direct relationship. So of course, meaning, and it's mainly going to be the temperature, of course, that we're going to be changing, right? You usually have outside control of your temperature. So as our temperature increases, then our volume must increase as well, or vice versa. And so this is the formula. I just like rewriting it. So V1 over T1 equals V2 over T2. So again, write that start. But like I said, it'll all become more clear once we look at the combined gas laws. And so it says that the volume of a gas is directly proportional to the absolute temperature. And so this phrase, absolute temperature, is again why we have to always be in Kelvin. So I should have marked that up here. So again, temperature in kelvins all the time. So whatever you need to do, start it, whatever, bright lights here. And so according to kinetic molecular theory, when we increase the temperature of the gas, then that's also related to the average speed and thus kinetic energy of our particle. And so again, this is our, what we're saying kind of graphically. And then again, we have to extrapolate, since of course, going back to the physical reality of gases, so gases are going to condense into liquids before they reach that. So again, It's not a perfect relationship. And so again, what you're kind of taking away from the ideal gas versus a real gas is that kind of, moderate conditions, a real gas will behave just like this ideal gas with all these assumptions that we've made. But again, at these extreme temperatures like we're seeing when we start compressing it a lot and they're really close together and the physical size matters, or again, when we've condensed them so much that now they're going to be close, then obviously we're seeing deviations from our kind of ideal gas law. And so thinking about this from a molecular perspective, so of course if we increase the temperature of our gas, then the gas particles move faster, more collisions with the wall, more frequently, and then with greater force, since they should have, again, an average greater speed, velocity. And then if you were to, of course, try to keep the pressure constant, then the gas would have to occupy a larger volume, or vice versa. And so you maybe have seen this with a balloon. So you could fill a balloon, and then if you put it in ice water, it should shrink a little, and then boiling water, it would expand. But let's watch a video. So I like this video. Let's see. Oh, I'm actually signed in, so that's good. We won't have ads. Let me find it. There we go. Oh.
Hi everybody, I'm meteorologist Jay Birchback along with Carl Nelson at the Imagination Station. Today we're dealing with one of my specialties, air pressure, air pressure. And you may have seen this experiment before using a gas can or a smaller can. This is big scale. This is the Imagination Station's version of supersizing that experiment, showing air pressure which can crush this huge barrel. Carl.
So we got a steel 55-gallon drum here. I just want to give you a sense for how strong and rugged these barrels are. Jay, if you can stabilize the barrel, I take a sledgehammer and try to. If you relied on me to crush this barrel, we'd be here all day.
Sure.
That thing is pretty tough. So instead, we're going to use air pressure to crush this drum. So I'm going to lift this up. I'm just going to stick it on this can here.
That's it? Oh, okay.
That's what I'm going to do first. Add some water inside, about 6 cups of water. And what the water's going to do is we're going to create water vapor inside that we're going to heat up. Now water vapor when it's warmed up and air when it's warmed up occupy a little bit more space. Our goal is to try to trap some of that expanded air and water vapor inside. We're going to seal this up and then cool it down.
Okay.
You should see some crushing action at that point. But first, we're going to need to heat that air up. So help me flip this up on the stand here.
Okay.
The thing I'm looking for, Jack, is we want to see a nice, solid stream of steam coming out of this opening here.
Sure.
And in order to do that, you can't just use like a blowtorch or anything small. As this is the supersized version, we're going to use one of these road torches.
Yeah, I think I'll back up.
Okay. So it'll take a few seconds here to get the water warmed up inside the barrel. But to give you an idea how big the flame we're going to work with. There's a good sort of jet of steam shooting out over here. We're going to try to capture that.
Okay.
Back in. We're going to wrench it down tight because we don't want any of that warm, expanded air to escape. But the key now, Jay, is wheel over that tray of ice. We're going to cool this baby down really quick in a tray of ice. Hold on. And this is good. Here are ends of the drum popping in.
There we go. There we go. So what we're seeing is air pressure literally crush.
14.7 pounds per square inch of normal atmospheric pressure now pushing down on this drum. And because that water vapor inside and that warm air inside has cooled down, taking up less space, doing a lot more damage than that sledgehammer did earlier.
That is amazing. Looks like a pop can or a soda can.
Looks like a pop can or soda can. Or if you ever rinsed out plastic milk jugs,
Sure.
and then you put the cap back on with warm water, stick it on the counter, you can see after a time they start to like collapse back in. Same principle, but it's a safe at-home way you can do it.
Sure. Yeah. No. You know, having that blowtorch for the experts like you, exactly. Well, this is really neat. A real 55-gallon steel drum crushed.
Yeah, so that was pretty cool. And so you could do that. I think they mentioned you can do the same thing with like an aluminum can or something not as dangerous. But again, same sort of idea, and thinking about how they got it to work, right? They made it spectacular since they heated up all that water. So they made it pretty extreme, right? They heated up water, got it all expanded, and of course taking advantage of kind of water's ability to recondense and liquefy pretty readily as opposed to other gases. And then you notice, of course, right, they had it hot and steaming, and then, right, obviously high temperature. So hot, high temperature. Obviously it was all coming out, but then they made it a closed system, which that was important, right? So then they closed the system, so their N was constant basically, so your N number of moles of water in that case, and then of course they cooled it down, and then again, given that water condenses pretty readily, they probably had hardly any gas, right, to fight against the atmospheric pressure, so hence why the atmospheric pressure just crushed it. All right, that's probably a good place for a break so you can see where we're going with the math. But like I said, we'll do a little break time. I'll put our formula back down here so we can pick it up. So V1T1 equals V2T2. So that's where we'll pick up after the break. And again, temperature in Kelvin for all those. All right, so feel free to take a 10-minute break. Like I said, I'm going to try to hand back a lot of your papers. I found some in my office I was sitting on and did some grading over the weekend.
Did you see my papers? Okay.
So I think most of you are kind of working through the problem. I just wanted to show the PhET simulation thing again. So of course, right, we can put some gas in there. So it gives us our initial conditions. So okay, like 9.5 roughly ATM. And then we can cool it down. And so you can see, right, our temperature decreasing, pressure decreasing. And of course, right, heat it back up. Do the same thing. And so then it mentions if we want to hold something constant, let me make this smaller. And let me cool it down for a second. And so if we hold our pressure constant, and then we're going to change volume based off of our temperature. So again, we can heat it and see how that volume expands to keep the pressure constant. And then of course, right, cool it back down, and again it's going to shrink back to keep pressure constant. All right, I'll let y'all take another minute just to finish up this. So first tell me what you get for x, so when you solve. And so hopefully you have something set up like this. So we don't have our first temperature, but we do have our final temperature and final volume. And so what do we get for our, like I said, initial temperature in Kelvin? So that's easier. So what do we get? Do we get about 297 Kelvin for our initial temperature? Yes, no, roughly. So yes, so X equals 297 K. And so notice Kelvin, right, does not have a degree sign. It's just Kelvin. And then let's subtract to figure it out in Celsius, so minus 273. So about 24 degrees Celsius. And so again, those are pretty straightforward, just as long as you do your calculations in Kelvin. So again, if you need to star that, whatever, that you have to be in Kelvin in this proportion formula, and then convert later. All right, so the last kind of simple relationship or simple gas law is Avogadro's, and it's pretty straightforward, or again self-explanatory. So volume and moles have a direct relationship, again holding everything constant. And again, that makes sense. So if you have more gas molecules, they'll need to fit in a larger volume. And so we can play with our PhET simulation and see that. So now we want to hold our pressure constant. And so if we add more, well, I wish I could hold more things constant. Yeah, so we want to hold pressure constant. And so of course, if we add more moles there, you can tell I'm pumping more gas in, and our volume keeps increasing to keep our pressure constant. Oops, okay, I exploded our container here. So again, right, pretty straightforward. And this is also key, again, for our ideal gas law. Some other relationships will come up from this, but equal volumes of gases contain equal numbers of molecules, so the identity does not matter. So we'll later see, right, this isn't perfectly true, but it's pretty much close enough. And again, right, we're treating all our gases like ideal gases. And so then we have our formula. So our volume 1 over N1 is equal to volume 2 over N2. And again, units wouldn't matter just as long as you're in the same volume measurement. And so again, if we're trying to hold our pressure constant, obviously if we increase the number of gas molecules, more of them will hit the wall. So to keep the pressure constant, the volume must increase, just like again we saw with the little FET simulation. All right, so let's try this practice problem. And so now we have that a male athlete has an initial lung volume of 6.15 liters during a deep inhalation. And so at that volume, the lungs contain 0.254 moles of air. During exhalation, the volume decreases to 2.55 liters. And then just pay attention to what they're asking for. So how many moles of gas does the athlete exhale? So what did we get for our answer, and also what were they saying? So if we set up our problem, so of course we had our initial volume and initial moles, and then they told us what we decreased to. And so what did we find for N2 in this? So 2.55 times 0.254 divided by 6.15. And so do we get that number there? And except what's this number though? This isn't our final answer, right?
It's the moles of gas after.
Excellent. So it's moles, right, in the lung still. But then they asked us how many did he exhale. So then we need to do a little subtraction here. So 0.254 minus what was remaining now. And so about 0.149 moles exhaled on that one. Questions on that one? All right, so those were our kind of simple gas laws. But now let's combine everything and look at our ideal gas law. And so now our ideal gas law puts all the different factors together in kind of one formula. And so we'll look at this. And so we have this ideal gas law, PV equals nRT. And so let's go through these variables. So of course, P is for pressure. And so now this is where the units do matter. And they matter because of our gas constant here. So the reason why I'm telling you we have to be in ATM, and then our volume has to be in liters, N is in moles, and T is in Kelvin is because of this ideal gas law constant. And so let's look at what I mean by this. So if you were to just Google gas law constant, let's look at what it brings up. So, okay, we have our gas law constant. And then, oh my goodness, if you look at it, right, there's like a billion different gas law constants. But now we see why, right? So that the constant depends on whatever unit we're in. So later, for example, or in other applications, I can't remember necessarily. We'll do it in this class. I think we will. But sometimes we have this other unit of R when you're talking about energy. So this is joules. But that's not the one we're in. So right, again, there's other units for pascals, for bar, for ATM per feet cubed, right? So there's all these different units. But let's find the one we're in. Liters, ATM, Kelvin, mole, right? So this is the one we're interested in. So here is the 0.0821. So of course rounded, right? This one reports out to more significant figures is all. All right, so I want you to understand where the gas law constant comes from. And like I said, if you ever look it up independently, you need to find the one that matches with ATM, liter, moles, Kelvin. And so that's why. Excellent. So there's our R, which like we said is a constant, which will help us later. And so now it's kind of showing us how to rederive the simple laws. But let's kind of go through that together. So again, we're given this new relationship of PV equals nRT. So again, R is a constant. And so if R is a constant, we can rearrange our formula to P times V over N over T equals R. And then this is, of course, valid for any other set of conditions of pressure, volume, moles, and temperature. So it always has to equal R. And so now we get to what I call kind of like our combined ideal gas law, which is a great formula. So then you end up with P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And so I might write this down, star it, highlight it, because now you can derive all your simple gas formulas from this. So can derive all other formulas. Or what you find too is you could get into a more complicated problem where maybe they're changing 3 variables instead of just 2, and it doesn't matter however many variables, or all 4 could change, right? But as long as you can set up this relationship, then you can find your answer, or like I said, derive the other gas laws based on what we hold constant. So again, kind of going back to these laws, so right, Boyle's laws, that's when we hold our number of moles and our temperature constant, so then we get, right, our P1 B1 equals P2 B2 back out. Same thing with Charles, so you're holding pressure in moles constant, so that's where we get our volume temperature relationship. And same thing, Avogadro's, right, you're holding everything constant except for volume and moles. But like I said, we can have problems with 3 variables now, or 4 even, and still get our relationship. And then, like I said, we also have our PV equals nRT then for this scenario if we don't have before and afters. So now let's try this kind of practice problem. So calculate our volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atm and 315 Kelvin. And again, R is 0.0821 or our atm liters Kelvin. So try that out. So these problems aren't too bad. So of course, right, just rearrange to solve for volume. So volume equals nRT over P. And so what do we get for volume then? So did we get about 15.95 liters or 16 liters roughly? See, yes, yes, excellent. So right, not too bad, these calculations. Just make sure you're in all the correct units and everything. And so I think that we technically rounded up to 16 with 3 sig figs there. Questions on this one? So hopefully the math isn't too bad. So pretty light on the math. And so now let's look at what I call these little tips and tricks later. So this might help us with other problems that could seem difficult, but we have these relationships. And so of course, again, right, we're seeing obviously our volume of our gas can vary widely with our pressure and temperature. And so chemists have come across these standard conditions which we report measurements so we can compare. And so our standard pressure is 1 atm, standard temperature is 273 Kelvin or 0. Standard amount is 1 mole. And so this is kind of what's key, is our standard volume then occupied by 1 mole of substance is 22.4 liters. So I would write that down, star that. So again, 1 mole at STP, 22.4 liters. And so we can also say, okay, well, if this is our molar volume, then we also have 6.022 times 10 to the 23rd molecules. So, right, this is just Avogadro's number. So just kind of helping you see different, easier relationships. And again, it doesn't matter the identity of the gas. They all occupy the same volume. So they would have different densities, right? So we can appreciate that obviously helium is only 4 grams per mole, and xenon, I don't have xenon's weight, but xenon is obviously a lot heavier. So right, xenon will be more dense, but again, they're all occupying the same volume. All right. Other things, so we get into partial pressure, which I think kind of sounds more complicated than it is. And so all we're saying is that our total pressure of a gas is the sum of our partial pressures. And so this kind of goes back to our kinetic molecular theory. Again, we're assuming that they do not interact, so identity does not matter. And particles of different masses have the same average kinetic energy. So that's kind of the key. So they have the same kinetic energy, and so our total pressure is the same. So then we can figure out the pressure of a single gas, which is known as a partial pressure. So again, kind of going back to the composition of air. And so we'll look at this, but basically we can either figure out the fraction of it and compare it to the total pressure, or if we know kind of the moles of gas, then we can figure out the partial pressure. So you could figure out kind of the mole percentage there. And so again, key points is that our total pressure then is equal to the pressure of our component A plus B plus C, yada, yada, yada. And again, these gases behave independently, and we're assuming no interactions. And so this is kind of the derivation of it. So again, we're saying since it's really dependent upon our total number of moles, then our pressure is additive here. And so then we can calculate our mole fraction. So it's just the ratio of our partial pressure a single gas contributes to the total pressure. So just finding the mole components, so you could find how many moles of, let's just say A, and then you take it over the total moles, so A plus B plus C plus D, etc., and that gives us our mole fraction. And so this is kind of what we're more familiar with. So again, if we know the component, so we know that nitrogen has a 78% composition of air. So if we know that we have a total ATM pressure of 1 for our atmosphere, so converting a percent to a decimal gives us 0.78 ATM. And then of course, if oxygen is about 21%, then we have 0.21 ATM from oxygen, 0.01 ATM from argon, and then obviously other negligible gases. All right, so then we'll look at some math here, but let's try a problem. All right, so let's see. Let's try a problem really quickly. So at STP, what is the volume of 1.085 times 10 to the 21 moles of nitrogen? So see if you can figure out the trick for that. So the question is, did we find the trick to make this easy? And so kind of going back to the previous section, so okay, they gave us a hint. Our standard volume, 22.4 liters. But instead of using moles, I would make it even easier on yourselves, right? And say 6.022 times 10 to the 23rd molecules of gas is 22.4 liters. So now let's set that up. So just setting up a proportion here. And so this just helps you from doing kind of multi-step. So, you know, you could have solved moles first and then gone from moles to volume. But like I said, this trick just kind of helps you do it a little faster. Just seeing all those relationships. So times 22.4 divided by our Avogadro's number. And so should have gotten something like 0.0404 liters there. Is that what we got for that one? Excellent. All right, so we're going to be kind of shifting a little. I was trying to grab some stuff from the stock room, but I may have to go back. Forgot my key. So let's start shifting. So right, the first half, so we talked about gas laws. Now we want to look at the phase change. So I know we touched on phase change in our lab. But we'll also be looking at now our intermolecular forces. So again, just kind of appreciate this shift, right? So we started with ideal gas laws where we said, okay, intermolecular forces don't matter. But now we want to say, okay, they really do matter and they do dictate different properties. So we do want to analyze that. And so we'll get to the math of the phase changes. That's probably like the most intense math you'll have to do in here. But like I said, we'll build to it. And so again, we can think about water, and water's just good because we can see it in all three phases, so we can appreciate this. So again, obviously you know you can add heat to water and it goes to a solid, liquid, and then ultimately steam. But then what we kind of want to answer is, well, why is water, you know, a solid, liquid, gas at basically all of our normal temperatures? Kind of what dictates these properties? And so now this goes into our intermolecular forces. And so inter is going to be between molecules, right? So kind of like your interstate highway, so that's between states. And so when we're talking about intermolecular forces and phase change, we're not talking about breaking bonds. So right, we're not breaking any covalent bonds. We're just disrupting those intermolecular attractive forces, which are obviously, right, a lot weaker than bonds. So I just want to make that clear. So right, again, you heat up water, right, you're not breaking any covalent bonds or anything that would take much more energy. We're just doing a phase change. And so then blah, 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 just kind of setting us up. So again, all attractive forces are electrostatic in nature. We've kind of gotten a sense of that. So we've talked about ionic compounds. So those are obviously electrostatic, right? You have one positive part, one negative part. and that's what holds it together. But now we're going to look at other attractive forces, right, that maybe are not so extreme. So again, right, the ionic compound is very extreme because you have a positive and a negative part. But what happens basically to the strength of those attractions when we don't have such quite a difference, right? But we still have forces, so we'll look at those. And so that is what dictates the properties then. So then we're saying at room temperature, moderate to strong attractive forces result in materials being solids or liquids. And so now we can start to think about other substances or things we've used in lab. So of course, like drugs, small molecules like aspirin, right, those are powders. But then we're going to find that they have pretty relatively low boiling points, again, right, in context with kind of the ionic compound. And then, right, we have this statement here, which we'll dive deeper into. So the stronger the attractive forces, the higher the boiling point will be and the melting point. So again, now we're starting to see why substances are liquids and some are gases at room temperature. And then obviously these attractive forces vary. So again, we'll go through them and look at the types of forces in our particle. And so obviously, again, the stronger the attractions, the more energy it takes to separate them. And again, we're not breaking bonds, just separating molecules. I'm going to say separating molecules so we're clear. And I'm only emphasizing this because I've seen, CHEM students struggle with this concept and say it incorrectly, right? So we just want to make sure we're making the distinction that we're not breaking any bonds here. And so again, it emphasizes that yes, we're overcoming the attractions between the particles, but we're not breaking any intramolecular forces. We're not breaking any covalent bonds. And so now we want to go into those electrostatic forces. So again, we're fundamentally asking, why are molecules attracted to each other? And so like we've been saying, okay, they're due to opposite charges. We understand this with our extremes, so our cation and anion. But now we're going to be looking at polar molecules. So we've kind of identified polar molecules, but what we want to take now is, what does that mean if something is polar? And we'll get into that, right? So kind of thinking of where we're going, where we have a partial positive and partial negative N. And we'll look at how nonpolar molecules have what are called temporary dipoles. And then obviously larger charges, so this is again more evident in our ionic compounds, stronger attractions, and then longer distances result in weaker attractions. And then again, once again, emphasizing that these are small relative to our bonding forces. All right, so first we start with our weakest. So these are our dispersion forces, also called London dispersion or van der Waals forces. So I'll just write down all the other alternate names. And so this is caused because of a temporary dipole. And so let's look at the picture because I think it makes more sense than looking at all the text. And so let's just say we're looking at a helium atom here. And of course, right, our helium atom has two little electrons floating around. And so let's just say, what if we took a snapshot of it? And it just so happens that at this point in time, our electrons are on one side of our molecule. And then that could cause what's called an induction or induce, right, a temporary dipole in our other one. So basically, right, if we have a little negative region here, we could again take this snapshot and see that its neighbor also has a negative region on the left side. And right, this could be perpetuated, so it's showing us kind of 3 little heliums where this has happened. And so in this case, right, we're seeing, of course, where the electrons are, creates a region of temporary negative electron density. So we have, right, negative, partial negative on our left side. And then obviously where the electrons are not leaves us with this partial positive. And so that instantaneous interaction here gives them a little bit of attractive force. And then obviously, right, this is going to keep moving. So this is just a kind of temporary attraction, and then obviously these will keep circling our nucleus. So very weak, obviously. And then let's look at some effects that would increase our dispersion forces. And so, of course, we're going to compare our noble gases. So you might recall that our noble gases are going to be nonpolar, right? So they tend to be non-bonding. So then they're going to be nonpolar, just hanging out by themselves, right? And so looking at these, we can appreciate this boiling point. So it's size dependent. And so let's kind of look at why that is. So as our molar mass increases, so of course our electron cloud increases. And so this larger electron cloud is more polarizable, so it can have a greater strength. But again, that being said, right, all these noble gases are obviously gases, and they have still relatively low boiling points. So of course helium is super extreme, 4.2 Kelvin, and we could get into, right, this is why helium at least was used or is primarily used to cool down like magnets. So like NMRs require helium to help get down to the correct temperature, although that being said, they're making new modern NMRs that do not require helium and can instead just run off of nitrogen, which is not so extreme. And then obviously, right, xenon, so our heaviest noble gas, still has a boiling point of 165. So again, right, it's going to be gas at room temperature. And so again, just appreciating as our molar mass increases, our boiling point increases. We can also look at the effect of shape. So again, I won't ask too much of you in this class, but you should at least be able to distinguish, let's say, between like pentane and neopentane, and appreciate that the straight chain alkane should have a higher boiling point due to the larger surface area. So right, you can kind of imagine how they stack really nicely there, and of course, right, all that surface area for intermolecular forces versus this neopentane, right, imagining another molecule coming across, obviously a lot less area for interaction. And so when you're comparing two molecules and kind of their relative boiling points, so of course you're going to start off with the molar mass. And obviously we're looking at this scenario since they have the same formula, so they would have the same mass, so C5H12 for both of these. All right, so no difference on the mass there, so that's why we have to look at the surface area, molecular shape argument. And so again, at least appreciate how much of a difference that makes. So pentane, still pretty relatively low at 36 degrees Celsius, but right, neopentane at 9.5, so that would be, right, a gas at room temperature. And those are other considerations to make when you're trying to pick appropriate solvents or anything. So pentane is a really good low boiling solvent if you need something to boil pretty low. So again, 36. And obviously neopentane would not be very useful, right, at 9.5. How would you work with it? That would be a pain. So chemists, right, they want to work with things that are going to be a liquid reagent, things that are easier to add. Again, right, as soon as you start trying to mess with gases, that's an added layer of complication. And it's more like a safety thing, too. And so now this chart is just helping us appreciate the molar mass trend. So these are all straight chain alkanes. The only difference is we're adding a carbon. So again, appreciating increasing boiling point. There's octane for kind of reference, since again a lot of fuel contains octane, but again it's going to be a mixture of different hydrocarbons of different chains there. So again, nice to appreciate the trend. Oh. Okay, we're kind of running out of time. And then, like I said, we won't get too nitty-gritty into this at the 100 level. This would be more like OChem level anyways, where they're like really trying to trick you with branch chains. But we just want to appreciate that any sort of branching will cause it to have a lower boiling point. All right, so I guess we'll stop there, which is okay because I needed to grab some chemicals for a little demo. So we'll pick back up on Wednesday looking at more intermolecular forces. I'll grab the stuff for the demo. And then of course we'll look at any other gas law math if we need to. And then yeah, we'll have our quiz on Wednesday too, like normal. And otherwise I'll see you in lab. So let me know if there are any questions on stream before I stop it. Oh, and then double check your grades. Just make sure everything was entered in properly. I don't know why I always have issues with, especially with Blackboard Ultra. I swear it's even more finicky. But yeah, just make sure everything's in there. If there's any straggling assignments, just let me know. Trying to get the grades all accurate.